Yeah.
Fine. Okay, so yeah, now we have Prashant Panigrahi, and he will be talking on zero width resonance symmetry perspective. Yeah, Prashant, please go ahead.
Yeah, yeah. Okay, so first of all, thanks Bhabani and Manas. It's a pleasure to be, see each other at least in these pandemic days, and hope all of us will meet in better times. So I'll be talking about zero width resonance. Exceptional point, you have had a lot of beautiful talks, including that of your guest. So zero width resonance is another very interesting thing. I think it will have a lot of applications later. So I am going to look at it in the context of this post-Taylor potential, which was used yesterday as a solution of complex solution of the KdV equation. So you have seen this kind of thing. So, the organization of the talk is like this. So I will be using both PT-symmetry and supersymmetry. You will find that supersymmetry brings a nice perspective to these kind of systems because this has been solvable using supersymmetry. So it gives us access to phases of supersymmetry, namely broken supersymmetry, unbroken supersymmetry, broken PT, unbroken PT. And the model which I will be choosing, this complex car potential, which was yesterday introduced in the context of solitons, namely that of KdV equation, is exactly solvable, shows all this behavior, and there is a beautiful symmetry there which connects all these aspects. So it can also have the optical connection because you can actually realize them in Helmholtz equation, and for example, without this complex part, it has been already realized. There is a patent by Professor G.S. Agarwal and from University of Hyderabad in the context of reflectionless potential. With this complex one, hopefully some similar kind of applications will emerge. Now, you will find out in the complex domain where the energy eigenvalues will become complex at a very specific point where the amplitude is an integer. You will have the zero width resonance where this reflection r mod square plus t mod square will be 1. And amazing thing is that you have exact wave functions for that because of this solvability of complex car potential. And you will see some interesting features there. Now, yesterday there was talk about this KdV equation, and as you know, this scar potential has deep connection with KdV equation. And I point out those things. For example, isospectral deformation of scar potential gives rise to solitons and multi-solitons. And you will find a beautiful introduction to this topic in the Supersymmetric Quantum Mechanics book of Khare, Sukhatme, and Cooper. And then finally, I will summarize with some conclusions. Okay. Now, this has been already introduced to you just for the sake of completeness. So, in conventional quantum mechanics, we are familiar with Hermitian Hamiltonians with real eigenvalues, and as you has been pointed out very explicitly, you have matrix examples, of Hamiltonians like two-level systems, three-level systems. For matrix kind of things are well understood in the sense that, as Professor Bender pointed out, you have explicit matrices showing the property of P and T. So you have sectors which have real eigenvalues. You understand these things. In the case of continuous systems, things are yet to be completely understood. So explicitly working out things really helps. So PT symmetry is x goes to minus x, I goes to minus I, and if the Hamiltonian is symmetric, interestingly, when if it is complex, you get real eigenvalues. A very simple example which has physical interpretation is that you will look at harmonic oscillator and have a shift I alpha x. You know that you can redefine a variable y using x minus I alpha, and the whole thing goes through real eigenvalue. And what you find, the ground state, for example, is a shifted Gaussian with imaginary shift. What's the physical meaning of the imaginary shift? You go to the momentum space, Gaussian remains a Gaussian, the shift in imaginary shift of x becomes a real shift of the momentum. So you have a physical picture that yes, here this I, this complex things means that you are actually having a localized, momentum localized wave function. And you can do quantum mechanics both in real space and in momentum space. So nothing very big deal. But the same is not true and needs much deeper understanding beyond these kind of things where you have a shift in momentum, because if you have nonlinear things like Ix cube, then also you get real eigenvalues. So, much deeper understanding is required for continuous variable systems. So, more than generically, these are the kind of things people have already pointed out. For example, if you have a cubic pillow, then you will have complex eigenvalues. Unbroken case will have real, broken case will have thing, and these are the papers of Bender which started this field. And the spectrum shows this kind of behavior. Unbroken PT, broken PT, complex eigenvalues, complex conjugate pairs, and this boundary point is the exceptional point. Now, as Jogesh pointed out, there have been many papers now, PT-symmetry, realization of PT-symmetry. I have only mentioned a few things here. The works of the Christodoulos and many other things. PT-symmetric lasers are there, and interestingly, supersymmetric things are there. So hopefully, the combination of supersymmetry and PT-symmetry may throw some more light. Okay, now I am using supersymmetry because I have used those kind of things to solve this model. And it throws light on solitons, isospectral deformation, many other things. So in supersymmetry, you write the potential in a way that it can be cast in this form. There is this function W called superpotential. So the potential can be written as a square with a derivative. This is actually dw by dx, w square plus dw, not second derivative, it's a mistake. dw by dx. W is the superpotential. Now, the good thing is that the moment you start writing this way, you get a bonus. If this Hamiltonian is minus k dagger k, you get k dagger. There's a nice intertwining property that if you can solve this Hamiltonian, you can also solve this Hamiltonian. So this is of course known to mathematicians like Darboux, and if you see, for example, in Freeland Hall, this factorization was started by Schrödinger. This is well known. Mathematics literature was well known. And in the context of supersymmetry, it really started in the 80s, thanks to the paper of Edward Witten. And then the observation of solvability and shape invariance really gave a very big boost to it. Many in India like Khare, Bhabani, and many other people have contributed significantly to this area. So this is superpotential. If you know the ground state is a log derivative, d by dx of log of this thing. And this factorizability allows you to solve the system in terms of a fast order differential equation and intertwining, like kind of thing which in oscillators, slightly different, but you can actually solve systems and cast new light on solvability. But okay, so just to briefly mention, this Gedenstein is the person who pointed out about the shape invariance. Namely, if the potential V plus, which is your particular potential, if it can be cast with like a V minus, the potential where you started, with a new parameter. For example, if you look at a hydrogen atom, you will find out L is the parameter. So if this is L here, this will be like L plus 1, plus a constant. Then this problem can be solved. And more formally, there are a lot of review articles. This entire eigenvalue can be solved through writing V minus as again V plus, and using this thing, and so you will get a sum. So very beautifully, for example, you can guess that take the hydrogen atom, you can guess knowing the potential, which is like 1 over r times L into L plus 1 by r square. You can actually guess what is W. W would be something like L by r plus a constant, as simple as that. And the moment you factorize, ground state energy will come out, and use this trick to solve the hydrogen atom in the quickest way. And you immediately, factorization gives you the ground state energy, which is non-perturbative. So beautiful things come out, and you can solve a huge class of problems. In fact, the list which are there in the Imperial Hall can be solved using this and new examples also. Okay, so now I will be looking at optics, Helmholtz equation, partly to avoid inner product, the problem of inner product. And so here, in case of optics, this epsilon is your dielectric constant. It's the distribution here. So, and this can be cast like a Schrödinger equation, as has been mentioned earlier. Now, so anyway, these are all formal things. Now let me come to this thing that you can have a refractive index which will have PT-symmetry. Now, PT-symmetry allows you to write, for example, for this curve case, in the form of two constants, V1, V2, and one I here. Tan hyperbolic is odd, because of which when I goes to minus I, this fellow X goes to minus X. This potential reflects PT-symmetry, as long as V1, V2 are real. So as I mentioned to you, without this object, the imaginary part, this was there is a patent where it has been used. This designed refractive index has been used for reflection, controlling reflection. So I do not know if that patent has become technology, but in principle, you can have glasses with the designed refractive index to allow light to go in or not to go in. So this problem was explicitly solved by Jafar Rahman, beautiful piece of work with this thing, and energy eigenvalues, wave functions were explicitly written down by him. So what we did, I have given reference to this work that my student Kumar Abhinav, who is now a faculty in Thailand, he cast it in this form. He pointed out that if you can write this complex superpotential in form of two parameters, A, B, and something called CPT, rewrite those potential which I given earlier, then it shows some interesting point. What is that? That you find out that in order that the potential will become PT-symmetric, a condition has to be satisfied. Namely, CPT times something else is equal to 0. This A and B are the parameters of the potential. Alpha is the scale factor, which is alpha x, and CPT is the factor which we have introduced here, which you can write in terms of V1, V2 as you saw earlier. Now, what it does is that the phase where it is the real eigenvalue is the case where CPT is equal to 0. And the complex eigenvalue will be characterized by CPT non-zero. So two phases very neatly separate out if you parameterize the potential in this way. This analysis of physics paper quite some time back, it in fact emerged while solving this potential in the class. And this actually, and what you observe is this: there are this CPT can have plus minus kind of thing, and that would be related to V plus V minus. Okay. Now, when CPT is equal to 0, the PT-symmetric case is cast in this form. There you observe that, in fact, because of this parametric freedom, namely, if you shift A to B minus alpha by 2, potential is invariant, because of which you can find there are two superpotentials giving rise to one unique potential, this parametric freedom. So explicitly, W1 is here, W2 is here, and what it does is, it gives you two levels. As if, because as long as W1 and W2 are separate, you have two different kind of quantum systems with the same potential. Wave functions are different. You compute the energy. You find one case energy A minus n alpha whole square. It's a bound state, negative. The other case B minus alpha by 2 minus n by alpha whole square. This was in fact noticed by Quinn and Bakchi. And in fact, we had not noticed this point. They wrote a comment about it, and after that we realized our complex part was fine, but the real part we had missed out on this thing. So now, this in fact, I'll elaborate a little more later. So you will find out that there is.
Prashant, I can ask a quick question here. Yeah. So the system will have two grounds, degenerate ground state in this case?
No. Degenerate ground state will be there when SOCI is broken. Otherwise, I'll show you that picture. There will be equation something like A square by alpha square, B square by something equal to 1, which you can tune to choose the ground state. And there is a place where there is supersymmetry will be broken. That case there will be degeneration.
Okay.
And this SU1 symmetry was noticed by Quer and Bakchi. Okay. So as Bhabani asked, let me right away go to the broken unbroken cases. You find there are three domains. They are all explicit 4 domains. This corner is the one where SOCI is unbroken. Everywhere else it is broken, and they separate out into 3 different kind of things. This broken case, when the potential was real, was studied by this group of Khare, Sukhatme, Osim, Gangopadhyay, and they in fact pointed out a very interesting property that still there is a shape invariance here. If you do first change A to minus A, B to minus B, and then after that you do shape invariance in the regular way, you can generate the spectrum. Because as you all know, as Bhabani pointed out, that broken case, both the eigenvalues will coincide. Using standard supersymmetry, shape invariance is not possible. But as you also shown earlier, that this trick allows you to avoid that problem. And in fact, you use that to solve it here, also for the complex case. So, okay. So now, various domains you can systematically analyze, and no need to elaborate here. But and you use the trick which I pointed out earlier to solve for these things. That use this shape invariance, modified shape invariance, and you can map that broken case to a non-broken case plus a constant. Okay. So now go to the more interesting case of when the broken supersymmetric, broken PT-symmetric case, CPT non-zero. And in this case, A is fixed, the parameters are connected. There is no such freedom, A is equal to B minus alpha by 2. So again, you find here the same thing, two superpotentials giving rise to unique potential. So that explains why, for example, but with two different energies, plus minus I is coming. So that tells you why when there is a broken PT-symmetry, you have complex conjugate eigenvalues and wave functions are also complex conjugate. You find because of this thing, these two superpotential means two wave functions. So here it is. Now, okay, so this paper is also there earlier. Now here, we have explicitly wave functions are this very nice structure. If you for example, look at the Wigner function and those kind of things, this text structure gives you very beautiful pictures. And they're all in terms of this Jacobi polynomials with imaginary argument. Okay, so now what you observed is a very interesting thing. So we know for the Schrodinger equation that a conserved current. So typical thing is look at the Schrodinger equation, takes complex conjugate, and you find out d rho by dt plus divergence of j is equal to 0. Then you ask here, because my potential is complex, what can I do? What you find here, there's a conserved correlation. So the implication of the conserved correlation has been worked out with Professor Jainabar from IOP and Kumar. It's also an answer of his paper. And interesting function is that this thing that is conserved is a correlation, psi star minus x with psi of x at all time t. So that current, that correlation function is something which is conserved. Okay, so now what does it imply? You will find out that it has implication for the norm. In the unbroken PT-symmetric case, it has implication for scattering, and you can draw some conclusion that you need both the modes for in the scattering case, and certain cases which was observed experimentally was also found out for scattering matrix if you use this conserved correlation, details of which are here. Okay, just for the case of norm, you find out that this eta norm, that eta that comes out through this, which was earlier pointed out in many of these papers. All right, so now, so you find out the correlation and how it behaves for different value of CPT. Okay, now in general, when you look at R and T, and this reflection and transmission coefficient, which was pointed out yesterday, you find that R mod square plus T mod square is not equal to 1. There are problems here, but first you observe one thing, that when B goes to plus minus IB, it is 1. Now what happens B goes to plus minus IB? This is not PT-symmetric because you have a sectant form without I, but that problem is also solvable. It was in fact solved earlier by, as far as I know, a paper of Kharesh and somebody else, and they have listed in their book. So that is solvable, not PT-symmetric, real eigenvalues, but R mod square, T mod square is equal to 1. So here is an example where PT non-symmetric model is also solvable with real eigenvalues and conserved things. So one needs to think a little more carefully about solvability and PT-symmetry. All right. Now here what you find is that zero with resonance R mod square plus T mod square is equal to 1, even if the potential is complex. All right. So now you can see that that energy when A is equal to n alpha, what you find is that this spectrum was A minus n alpha plus I CPT whole square, and there was a negative sign in the front. At A is equal to n alpha, A minus n alpha goes. So you have I CPT mod square, I square is equal to minus 1, energy becomes positive. So you can exactly see that is a zero energy resonance because it is positive energy when at one point A is equal to n alpha. Namely, this integer A by alpha is integer. And as you know, for example, post-stellar potential has connection with angular momentum, L. To be more precise, if you take, for example, PLM cosine theta equation, and you define cosine theta is equal to tan hyperbolic x, it was noticed by Gurse and many other people that this angular momentum L square PLM cosine theta is equal to L into L plus 1 goes over to this eigenvalue problem where m square becomes the energy. So this A there becomes L, angular momentum integer is well understood. So in the context of here, one needs to see this kind of analogy, the origin of integer a bit more carefully. I am not very clear in the complex case what happens, but if it is real, it's very clear that an integer thing comes. So this also is the condition, but you can see advantage of putting it in the form of that parameterization CPT, so that this condition which was obtained earlier by Jaffer, looks much more complicated. Here it is pretty simple why it arises in this way. Now you look at, for example, you see, at that point there's a lot of oscillation. You find that both the real and imaginary part, if you see, there is localization and a lot of oscillations. So it sort of reminds us of this. There are probably some physical things available here. I don't still quite understand what there is localization and huge amount of oscillation. So physical meaning still not clear to me. Okay. Now, to understand the physical meaning, one way is to go to Wigner function. For example, that's what we have tried. But here one needs to be a bit more careful, because Wigner function usually implies that some form of norm is there. Namely, if you take Wigner function, integrate over dx, you find that it becomes phi p mod square. So here, naively, if you take star, then it will not be quite proper to do. But since it is optics, I can still take a star, and Wigner-like function, I can see what happens in the phase structure. And you do see, interesting point is this negativity. And Wigner function negativity implies super quantumness. And what else does it mean in the context of optics? For example, I am not still very clear, but you do see this kind of negativity of the Wigner function. Okay. So now, coming back to isospectral deformation. So you will know that if you change the potential, superpotential by some function v of x, h minus will remain invariant, but h plus will change. So this is called isospectral because the energy does not change. In fact, the h minus remains same, that Hamiltonian remains same, but the h plus changes. Isospectral because energy does not change. It's a very useful method, and it has been used to generate n Soliton solutions. So we have also used it to generate some solutions in the presence of this complex potential. And in fact, it will match, some of it will match with all the unknown ones. Yesterday it was mentioned about Khare's paper. But if you want to remain h minus as same, one equation has to be satisfied, that is the Bernoulli equation. That connects this deformation to your ground state of the first potential. If they are tuned that way, then of course you will have a spectrum such that spectrum remains same. H minus is identical to the earlier one, H plus changes. All right. So now you try to do the same thing for the PT-symmetric potential. You find that Vx, the modification is this. All right. Now we know that there's a very deeper connection of this problem with KdV and modified KdV equation. For example, this V will satisfy modified KdV equation. And there are two different forms of combination which appears. One is v square plus minus derivative of v. One is v square plus minus iv, and both are solvable, and both satisfy KdV equation. The first one, for example, will give rise to the standard potential which Sukhatme and company have solved without I. The other one gives rise to these complex solutions. The fact that this KdV modified KdV connection has been published in this European journal paper, and you will find out that these complex things had appeared already in context of plasma physics, and you find again, apart from the sec tan kind of thing, you find solutions like Cn square plus ICN Sn kind of thing also as possible solutions. Those things are here. Periodic solutions also exist. Now, it was Bhabani asked about the ground state thing. In fact, you can check that this parameter A and B, which we analyze there, they satisfy this kind of equation. And so therefore you can tune A and B to find out whichever is the ground state. So now I'll not get into details. Okay. So you find a hysteresis kind of behavior. So let me see. Earlier the regions which I mentioned, region 1, region 2, region 3, these broken cases, they can be nicely studied from the simple equation. One case ground state is minus a square, the other superpotential is W1. The other case ground state is this. There is superpotential W2. You see this connection. So you can go from one to the other by tuning the parameters. This is the freedom which I had mentioned earlier. And now the other one, let me show you this isospectrally deformed potential also you can map to this. And the domain which I showed about this modified KdV and KdV, they appear in a very small domain, alpha 2 to 0. So then plot that, you see this plot. So basically one plot summarizes for you the whole different regions which we observed. There was a region of broken SOCI, 3 regions of broken SOCI, but different points about PT broken and non-broken. All those things you can combine here. You can actually see that the hysteresis kind of behavior, because if you go to one path and come back, you are coming back to a different point. So exceptional point will be here, and this point, that 0 with resonance is here. There will be 2 0 with resonance. They are all lying in the line. So I will not get into details, but these things are all clearly mentioned in our preprint, which we are also going to submit soon. Preprinted reference is also given there. Bhabani, how much time I have? Bhabani, are you able to hear me?
Yeah, you have time, 7 minutes to 10 minutes you have.
Okay, anyway, so I am more or less through. I will ask, wait for more questions. So in summary, that you have an exactly solvable system, and in terms of sec hyperbolic square plus some imaginary sec tan, which is not as simple as oscillator example where x square plus ix is exactly solvable, but yet this problem is solvable. It gives you, there are group theory behind it. There are SU11 cross SU11 in the unbroken PT sector, and giving rise to 2 different kind of energy eigenvalue problem. Because the superpotential is different, but potentially same. At the level of Hamiltonian, you have one system, but at the level of superpotential, we have 2 different systems. And that, for example, gives rise to this nested SU11. Now, on the other side, you find SL2C, because you go to the broken PT-Symmetric case, you find it is not SU11, it is SL2C. And as you know, SL2C and is a very sort of non-trivial kind of thing. In case of quantum mechanical problem, SL2C comes when you go from bound state to scattering state. And interestingly, it manifests here in the unbroken case. Now, sec hyperbolic square plus I sec tan has a much simpler version, sec hyperbolic square plus I tan hyperbolic. That is also solvable, both for real and imaginary part, and you do find same kind of features, 0 with resonance. Okay, so and exceptional point, at the exceptional point, you find that the wave functions become orthogonal. And this SL2C, this complex SL2C appears in that problem also. It has also connection with modified KdV and KdV. And amazingly, this modified KdV has 2 distinct versions. One is V square plus Bx, another is V square minus Bx, IBx. And both give rise to same KdV, but 2 different structure in terms of complex eigenvalue and real eigenvalue. So and as you know, isospectral deformation also in this case can go along 2 different directions. One giving rise to the regular sec hyperbolic square type of solution, another one giving rise to sec hyperbolic square plus I sec tan. So isospectral deformation, for example, if you look at more mathematically, has connection with so-called coadjoint orbit, area preserving diffusion regime. So I am sure these very simple examples what we study, if one looks at it very carefully, one can actually hopefully discover some more things. And I talked about only sec hyperbolic square plus I sec tan, but if you take, for example, Cn square plus I SNCn, that gives rise to band structures, which gives rise to periodic solutions of KdV. That also is tractable. Kind of things, for example, one we talked about was exactly soluble systems. There are versions of that in this case also. So now, and furthermore, you find that PT-symmetry and supersymmetry get intricately connected. There are parameter domains where both are present, and parameter domains show this kind of hysteresis behavior. So it's probably it may have some implications for technology, because the kind of things we talked about is optics. And without this eye, this potential has been already there in the refractometrics thing. As I told you, there is a patent on that. So hopefully some of these things will find applications. And that exceptional point, is something in the context of optics was pointed out in a PRL paper last year, I think, that light stops at exceptional point. You can actually control, because of the refractive index, velocity of light, so that you can really slow it down. So some of those things we are exploring, particularly, that how to store information and extract it by changing these parameters. So now, okay, so I'll stop here. And before I conclude, I would like to thank my collaborator, Aradhya Shukla, who is here, and Kumar, who is now in Thailand, and Subrajit Modak, and Adipto, who was a student here. So I think I'll stop here, Bhavani.
Okay. Thank you, Prashant, for your illuminating talk.